5-8, graphing absolute value functions. So our objective here is to graph an absolute value function and to translate the graph of an absolute value function. And we can quickly graph absolute value equations by shifting the graph of y is equal to the absolute value of x. An absolute value function has a V-shaped graph that opens up or down. The parent function for the family of absolute value functions is y is equal to the absolute value of x. A translation is a shift of the graph horizontally, vertically, or both. The result is a graph of the same size and shape but in a different position. So let's start this by looking at the parent absolute value function and what it actually looks like. So if I start with my function y is equal to the absolute value of x, anytime I want to make a graph, and I'm not sure what it looks like, I'm going to make a table. So let's plug in -3, -2, -1, 0, 1, 2, and 3 into my function. So if I plug -3 in for x, I just take the absolute value of -3 is going to be +3. +2, +1, absolute value of 0 is 0. And for positive numbers, we just get our same thing. So if I wanted to plot these points then, I would go -3, +3, -2, +2, -1, 0, 0, 1, 1, 2, 2, and 3, 3. And you can see that my graph is starting to look like a V. And if I graph the whole thing, I get a graph that looks kind of like a V. Okay. Now, what we're going to do with this function is, we are going to shift it. We are going to take this graph and we're going to move it up, down, left, and right. Okay, that's the whole graph, but you get the idea. So we're going to take this absolute value function, shift it up, down, left, and right. It's going to keep the same shape, but it's going to start in a different position. Its vertex is going to be in different position, and all the other things are going to be in different positions. So below is the graph of my parent function, y is equal to the absolute value of x, and y is equal to the absolute value of x minus 2. Notice here my vertex is 0, 0. Here my vertex is 0, -2. So notice that if I were to take this graph, pick it up, that didn't work, pick it up and shift it down 2, I would then get the same graph over here. Okay, so shift down 2, and I have my function on the right. Okay. How is the graph at the right related to the graph of the absolute value of x? Well, it's shifted up 1, 2, 3, 4. Okay, so this graph just shifted up 4. So what is the domain and range of each function in problem 1? Okay, so let's go back up here. So my domain for, let's look at my parent function. The domain for the parent function is how far left does it go, how far right does it go. The domain for the parent function is all real numbers because it never stops. That's what those arrows mean. It keeps going right, it keeps going left. However, the range is limited. The range, this is the lowest the function ever gets. So we can say that y has to be greater than or equal to 0. My domain doesn't change here. It's still going to be all real numbers, but my range does change. My range is now going to be y is greater than or equal to -2. Okay, because this graph goes up from -2. So the graph of the absolute value of x plus k is a translation of the absolute value of x. Let k be a positive number, then absolute value of x plus k translates the graph up k units, while absolute value of x minus k translates the graph down k units. So what we're doing is we're looking at that number right there, and we can see that here, that -2 shifted the graph down, and the formula for this graph would have been y is equal to the absolute value of x plus 4. So that 4 shifted the graph up 4 units. Okay? So when we look at this graph right here, y is equal to the absolute value of x plus 2, I could, if I wanted to, I could make a table, plug in all the numbers, and get my answers. Okay? Or I could say, well, I know that that point 0, 0 is on the parent function. Absolute value of y is equal, or sorry, y is equal to the absolute value of x. So that means if I shift it up 2, that point is on my new function. 1, 1 was on the parent function. Shift that up, shift that up, shift it up. And the same thing the other way. Okay, so now I was able to graph this function without having to make a whole table, without having to go through any of, uh, without having to go through a lot of work. For this one, now that, oops, this number right there will shift my graph down 7. And again, that's all that has changed from the parent function. So I get a nice couple lines, all with a slope, positive slope of 1 and a slope of -1, all right, to make this graph of this function. Now, if you can't do that, if you don't like that, of course, making a table is fine. If we plug 0 into this function, we get the absolute value of 0 minus 7 is -7. And we can see that's our first point. If I plug 1 in, I would get 1 minus 7. That would be -6. Okay, so you can see that these points will be produced when we plug these numbers into the function. The graphs below show what happens when you graph y is equal to the absolute value of x plus 2 and x minus 2. This is a little bit different because this function, the red function right there, is the graph of absolute value of x plus 2. And this is the graph of the absolute value of x minus 2. So while adding a number to the outside of the absolute value shifts it up and subtracting a number shifts it down, that's the opposite of what happens if you do it inside the function. So for a positive number h, x plus h translates the graph to the left, and x minus h translates the graph to the right. It seems to be a little counterintuitive, but if we plug in numbers, we can see that this actually works. So let's try this. Let's make a table, and let's plug in numbers. Normally, my first point, the vertex point, would be 0, 0. So if I plug in 0, I would get the absolute value of x plus 5. Okay, the absolute value of 0 plus 5 is 5. So that'd be 0, 5. Well, that doesn't look like it would be my vertex point. So let's plug in a negative number. Okay, so if I plug in a negative number, I would get -1 plus 5. That would be the absolute value of 4. If I plug in -2, that would be 3. Then -3, that would be 2. -4, that would be 1. And -5, finally I get 0. Now when I plug in -6, -6 plus 5 is a -1. The absolute value of -1 is a +1. So now you see we're going back up. So my graph is going boom, 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 and then back up. And I can see that by adding 5, I actually shifted the graph 5 to the left. This one, if I subtract 5, it's going to shift it 5 to the right. So now we can make a nice, quick, easy graph just like that. Now, this does get more complicated for absolute value functions that do other things, like have a number in the front, or have some sort of changed in number in the front here, or a number inside the absolute value in front of x. That would change the slope, and that becomes a little bit different, something we'll look at later. The absolute value function is an example of something called a piecewise function. A piecewise function is a function that has different rules for different parts of its domain. The rules for this part and the rules for this part are different. This part looks like a line that's going up. This part that looks like a line that's going down. And in fact, basically all we did was take this part of the line that would have been negative and we made it positive, which is sort of what the absolute value function actually does. Okay. For example, when x is greater than 0, the absolute value of x is equal to x. When x is less than 0, the absolute value of x is equal to negative x. It's going down and then it's going back up. That's what that's saying. Another example of a piecewise function is a step function. A step function is a function that pairs every number in an interval with a single value. The graph of a step function looks like a step, looks like the steps of a staircase. 1, 2, 3, just going up the steps. Okay. Each piece of the graph is a horizontal segment that is missing its right endpoint, indicated by an open circle. Because if it was closed, it would fail the vertical line test and not be a function anymore. So this function is going to be defined from there, straight open circle to there. Okay. So a school will charter buses so that the student body can attend a football game. Each bus holds a maximum of 60 students. Make a graph that models the relationship between the number of students X that go to the game by bus and the number of buses that are needed. Okay, so this graph is only going to have one quadrant because we don't need a negative, we can't have a negative number of people. So this is going to be number of students. And let's go, all right, we got 0, whoops, 0, 60, 120, 180, and so on. Okay. Then the number of buses. 1 buses. 1, 2, 3, 4. 1, 2, 3, 4. So if there's 0 people going, you don't need any buses. As soon as there's one kid who wants to go, you need a bus. And we're going to have the same number of buses up until 60 people. As soon as we have more than 60, we now need another bus. So it's that at 60 people, we don't need 2 buses. At 60 people, we still need 1 bus. But at 61 people, or anything less than that, we need or anything more than that, we need a second bus. All the way up to 120. Then you need a 3rd bus. Then you need a 4th bus. And then a 5th bus. And then so on and so on. And we have our step function that keeps stepping higher and higher and higher for every extra bus that we need. Okay. So last got a problem? Make a graph that models the relationship between the number of students X that go to the game by bus and the number of buses Y that are needed if each hold has a maximum of 50. Same idea. So we're going to get 0, 50, 100, 150, 1, 2, 3. This is students. This is bus. Okay, so 0 people, 0 buses, to 50, to 100, and then to 150. Okay, and then we have our, whoops, missed the step, step. So, how is the graph of y is equal to the absolute value of x minus 8 different than the graph of absolute value of x? It is shifted 8 down. Same shape, shifted 8 down. What is the equation for the translation 9 units up? That would be y is equal to the absolute value of x plus 9. That one shifted left 7. How are the graphs of x minus 4 and x, absolute value of x minus 4 and the absolute value of x minus 4 the same? They're both the same shape. They're both v's. They both have just a plane x, which means they have a slope of 1 and negative 1 on each piece of the absolute value. And how are they different? This one is shifted down 4. This one is shifted right 4. A student is graphing the equation absolute value of x minus 10 and translates the graph 10 units to the left. Minus means translate it 10 units to the right, not the left. And that was 5-8, graphing absolute value functions.